Right now, at this exact moment, there are 440 nuclear reactors quietly running across 31 countries, generating roughly 9% of the entire planet's electricity. Most people have never thought about this number at all. It is simply there, humming away in the background of modern life, the way electricity always seems to just exist. Now imagine every single one of them exploded. Not one reactor, in one country, on one terrible night in 1986. All 440, everywhere on Earth, at the exact same moment. What if the world had 440 Chernobyls in a single day? To answer this properly, we first need to understand what actually happened at Chernobyl itself. Because the popular image of that disaster, buildings vaporized, a landscape reduced to ash, is not quite accurate. And getting this part right changes everything about how we understand the hypothetical we are about to walk through. On April 26, 1986, reactor number 4 at the Chernobyl plant experienced a catastrophic steam explosion during a botched safety test. The explosion blew the roof off the reactor building and exposed the reactor core directly to the atmosphere. For the next 10 days, that exposed burning graphite core released a plume of radioactive material into the sky, carried by wind across Ukraine, Belarus, and much of Europe. The result was a 30-kilometer radius evacuation zone, an area now known as the Chernobyl Exclusion Zone, covering roughly 2,600 square kilometers, an area larger than the country of Luxembourg. Over 100,000 people were evacuated in the days and weeks that followed. The nearby city of Pripyat, once home to nearly 50,000 people, was emptied within 36 hours and has remained abandoned ever since. Now, multiply that by 440, occurring simultaneously. The first thing to understand is that not every nuclear reactor on Earth is the same design as Chernobyl. The Chernobyl reactor used a design called RBMK, which had a specific, dangerous flaw. Under certain conditions, particularly at low power, the reactor's safety systems could actually cause power output to spike rather than drop, a design characteristic Western reactors do not share. Most reactors operating today, particularly in the United States, France, and most of Western Europe, use pressurized water reactor designs with multiple layers of containment specifically engineered to prevent the kind of open-air explosion that occurred at Chernobyl. This matters enormously for our hypothetical, because it means a simultaneous global failure would not produce 440 identical Chernobyl-style explosions. It would produce 440 different failure events, varying dramatically in severity depending on reactor design, containment structure, and how the failure actually occurred. But let's assume, for the sake of this thought experiment, that we are looking at the worst realistic case. Every containment system fails. Every reactor experiences a meltdown severe enough to breach containment and release radioactive material into the atmosphere, similar in category, though not necessarily identical in scale, to Chernobyl. The immediate consequence would be a distribution of radioactive fallout that maps directly onto where nuclear power actually exists in the world. This is a crucial detail most people never consider. Nuclear power is not evenly distributed. The United States alone operates 94 reactors. France operates around 57, generating roughly 70% of that country's entire electricity supply. China, Russia, South Korea, and Japan collectively account for a massive share of the remaining global total. This means the fallout from our hypothetical would be devastatingly concentrated in specific regions, rather than evenly spread across the globe, hitting the northeastern United States, the Rhone Valley in France, the Korean Peninsula, and coastal Japan with extraordinary severity, while leaving vast stretches of the planet, entire continents without significant nuclear infrastructure, comparatively less directly affected by fallout, though certainly not unaffected by what would follow. Because what follows is where this hypothetical becomes genuinely civilization-altering, and it has almost nothing to do with the fallout itself. Nuclear power currently provides electricity to hundreds of millions of people across dozens of countries. In France specifically, losing nuclear power instantaneously would mean losing roughly 70% of the country's entire electrical grid capacity in a single moment. In the United States, it would mean losing approximately 18 to 20% of total electricity generation instantly, concentrated heavily in specific regional grids that depend on nuclear baseload power to remain stable. Modern electrical grids are not designed to absorb that kind of instantaneous, simultaneous loss. Grid operators typically plan for the failure of one, or at most, a handful of major generating stations at once, not dozens within the same national grid failing in the same second. The result would almost certainly be cascading grid failures extending far beyond the immediate vicinity of the reactors themselves. Hospitals losing power, water treatment plants losing power. Refrigeration for food and medical supplies failing across entire regions. This is the part of our hypothetical that would likely kill more people more quickly than the radiation itself, simply because modern civilization has become so deeply dependent on an uninterrupted electrical supply that even a temporary, localized blackout during extreme weather has historically caused hundreds of deaths. A simultaneous, massive, multi-country grid collapse would be a public health catastrophe entirely separate from anything related to radioactive contamination. Now, back to the radiation itself, because the long-term consequences here are genuinely fascinating, and not entirely what most people expect. The Chernobyl Exclusion Zone, nearly 4 decades after the disaster, has become something almost nobody predicted in 1986. It is now widely described by ecologists as the third largest nature reserve in mainland Europe. Wolves, lynx, wild horses, and European bison now roam through the abandoned zone, in numbers exceeding what existed there before the disaster. Because the one factor removed from that landscape more thoroughly than radiation ever could be is humans themselves, along with the hunting, farming, and development that comes with sustained human presence. Multiple long-term studies have found that many large mammal populations in the zone are, in the words of researchers who have spent years studying it, genuinely thriving. This does not mean radiation is harmless, and it would be irresponsible to suggest that. Radiation exposure carries real, documented risks, including elevated cancer rates among exposed populations and specific, serious health consequences for anyone exposed to high doses in the immediate aftermath of a meltdown. But the counterintuitive lesson of Chernobyl's exclusion zone is that, at a landscape level, the removal of ongoing human activity can, over decades, allow ecosystems to recover in ways that even significant radioactive contamination does not fully prevent. Now scale that lesson to 440 simultaneous exclusion zones scattered unevenly across the globe, wherever nuclear infrastructure happens to be concentrated. You would be looking at potentially tens of thousands of square kilometers of newly uninhabited land appearing almost overnight across multiple continents. Land that, decades later, based on everything we have observed at Chernobyl, would likely become some of the most ecologically vibrant, humanly untouched terrain on the planet. An entirely unintended consequence of an unimaginable catastrophe. But we should not let that long-term ecological silver lining obscure the genuinely staggering human cost of the scenario we are describing. Depending on how many people live within the immediate danger radius of each individual reactor, and this varies enormously, some reactors sit in fairly remote locations, while others, like several in the densely populated northeastern United States, and parts of Japan and South Korea, sit within a short drive of major metropolitan areas. The evacuation logistics alone would represent, almost certainly, the single largest simultaneous population displacement in recorded human history. Chernobyl's evacuation of roughly 100,000 people, coordinated by a single government with weeks to plan certain phases of the response, was already an extraordinarily difficult logistical undertaking. Now imagine dozens of national governments, many of them not accustomed to close coordination with one another, attempting to simultaneously evacuate populations numbering potentially in the tens of millions, all while their electrical grids, communication systems, and emergency services are themselves compromised by the same event causing the evacuation in the first place. This is ultimately the honest answer to our hypothetical. The radiation itself, while genuinely dangerous and with real long-term health consequences for millions of people, would very likely not be the deciding factor in how catastrophic this event actually became. The deciding factor would be the simultaneous collapse of the electrical, logistical, and governmental systems that modern civilization depends on to function at all. Systems that were never designed with the assumption that dozens of major failures might need to be managed at the exact same moment, in dozens of different countries, with no functioning power grid available to coordinate the response. 440 reactors quietly generating roughly 9% of the world's electricity right now. This very moment represent both one of the most tightly regulated, carefully monitored pieces of infrastructure humanity has ever built, and, in this entirely hypothetical scenario, a sobering illustration of exactly how much of modern life depends on systems most of us never think about, until the moment we are forced to imagine what happens if they all fail at once.